Okay, so just to recap quickly here, we're going through the first unit, possibly some of the second unit here. We talked about the difference between a function and relations. So relations are any set of data, so that can be table of values, set of points, equations, graphs. And then functions fall under the umbrella of relations, where each input has to have a unique output. In other words, I can't have the same x-coordinate matching up with more than one different y-coordinate. And we use f at x for function notation. So on a graph, if I'm asked to determine something like f at 6, we're asking the question, what is y when x is 6? So if I look along the x-axis here, and I find where y is 6, that looks to me, maybe I'm off a little bit here, maybe it is 5 or 6. I don't know, what do you guys think? Probably 6. Somewhere around 6 or 5.5. I would say probably 6. Okay, it's a lot easier, obviously, if you have the whole grid to look at. So what is y when x is 6? We could also be given an equation and asked to determine the equation at a particular x value. So of course, we know that just means we simply plug in that x value, and then we'll simplify from there. So if you have a perfect square here, you can square root it. If you have something that can be reduced, as far as like a radical that can be reduced, then you make sure you do that as well. This one, in this case, the square root of 9 is 3, and then 3 plus 1 is 4. So g at 9, or in other words, the function g, when evaluated at x equals 9, gives out a y value of 4. So x is 9, y is 4. All right, domain and range. We worked on setting up domain and range. So just as a reminder, this is how you set up domain. And we say x is from the set of all real numbers. And then we'll write something in this section that indicates any restrictions or boundaries on the x's. And then we'll close it up. If I have, so this is more for like a graph or an equation. If I have a set of points, it's much easier. All you need to do is you're going to say domain, and then you're going to say x equals, and then you will list the x's, lowest to highest, no duplicates. And then you'll close it up. For range, we'll do basically the exact same thing. So range for a graph or an equation will be the y's. So y is from the set of real numbers. Then you're going to create an expression in here with greater than or less than or equal to, and so on. That indicates any boundaries or restrictions on y. And then similarly, if we have a set of points, instead we'll just do y equals, and then we'll list the y's, lowest to highest, no duplicates. Oops. Does anyone remember the vertical line test? Colin?
So if you put the line straight up and it doesn't pass through twice, that's good.
Okay, so any vertical line drawn through a graph should only ever cross over that graph once if it's a function. Okay, so as an example, this is a function because any vertical line that I draw through here only crosses over that line once. Anything that sort of like overlaps itself, so if you see something like this, that's a good example. It's overlapping itself. This vertical line crosses over twice. Even though there's a vertical line that I can draw here that only crosses over once, This one crosses over twice, so automatically if there's any vertical line that can be drawn that crosses over twice, it's not a function. So we would say this one is a relation, but it's not a function. This one over here passes the vertical line test, so it is a function. Okay, so if we were practicing domain and range for a function, this is one of those functions that has those asymptotes that we talked about. So you're going to have to just kind of visualize where those lines are. So I'm seeing that our graph is sort of avoiding this area right here where x is -1. This is the line x equals -1. And I'm seeing there's a horizontal asymptote. It looks like it's right on the axis here, along where y equals 0. So when I state my domain and range for these ones, because technically these graphs, these should really have arrows on the ends. These graphs continue up and down forever and to the left and right forever. They just hop over those specific asymptote values. So for domain for this one, I would say x can be any number, except I don't want x to be equal to -1 because I know that there is a vertical asymptote at -1. So the graph hops over this area. It's never going to cross it. It will never touch it. For range, how would I say range for this? Can someone transfer that first example of this part? Sophia?
Y equals R, and then y equals 0.
Perfect. Okay, so that's domain and range for this one. For a set of points, this one's pretty quick, so we'll just do x equals, and then we list the x coordinates, lowest to highest. Don't duplicate any of them. So -1, 1, 2, 9. And then for range, we list the y coordinates, lowest to highest, no duplicates. So 1, 3, 4, 5, 6. Is this a function or is it not a function? Do I have more than one single x value matching up with different y values here? Are there any duplicated x values? Yes. Are they matching up with different y values? Yes. So not a function. I have one matching up with 1 and one matching up with 5. I can't have two or more of the same x matching up with different y's. So this is a relation, but it's not a function. Okay, if you have all unique x values, all your x values are different, automatically you can say it's a function. Okay, I'm not going to do partial factoring here because we didn't do that this semester, but I will go over quickly completing the square, because that's the first question on your review. So completing the square, first thing that we do is common factor out the a value. So I'm going to take that a value. Usually we bracket those first two terms. We take the a value out. So we don't take it out of the last term. So just the first two. We'll write what's left in the brackets. Second thing that we will do is we'll take that middle x term, whatever's in front of that, we divide by 2 and square it. And does anyone remember what we do with this number? Miguel?
Divide by 2 squared.
After that?
Add and subtract it with the brackets.
Very good. Okay, so we'll get 9 here. We're going to add and subtract this in the brackets. You have a harder version of this on your review package because you're going to use some fractions. But this is the general process. So for step number 2, we will add and subtract 9 in the brackets. I always do the subtraction second because that's the one that we're going to sort of take out of the brackets in the next step. So take out the last term in the brackets, the negative one. As you do this, you must multiply by whatever is in front, because technically this is being multiplied by every term here. So if I take out any one of those terms from the bracket, I must multiply it by the a value in front. So I'm going to take out negative 9, and I'll multiply it by, in this case, 2, because there's a 2 in front. So we're going to get 2x squared plus 6x plus 9 minus 18 outside the bracket. Okay, last two steps, add outside the brackets. So we'll say gather like terms outside the brackets. I'm just going to put that for brackets. And then the very last thing that we need to do, we just created a perfect square trinomial inside the brackets here. So we must factor this perfect square trinomial. So that's the very last thing. So I'll just put that down here. Okay, so when I factor something like this, there's a quick way to factor perfect square trinomials. We talked about this early on. However, you can always factor these regularly as well. So what two things multiply to 9 and add to 6? Multiplies to 9, adds to 6. Ella? 3 and 3. So technically I'm going to get x plus 3 times x plus 3, which will give me x plus 3 squared. So I always get two of the same brackets from a perfect square trinomial that I'm factoring. The quick way to do this is I know that I'm going to get two of those brackets, so I'm going to put it squared. I will put the square root of the first thing and the square root of the last thing in these slots, and I take the sign of the middle term and I put it in between them. This is also the middle term divided by 2. It's actually what you get inside here. You put that in here before you square it. So 6 divided by 2, or in other words, the square root of 9, because we're squaring it to get 9. So that's the deal. And again, don't forget that squared, because technically we have two of these brackets. We know that to multiply to 9 and add to 6, we get x plus 3, x plus 3 in each bracket. Final vertex here will be at hk. So if this is vertex form in ax minus h squared plus k form, the vertex is found at hk. So we switch the sign of what's in the brackets here. So this one will be negative 3, and keep the sign of this one as is. So negative 3, negative 14. All right, we'll do a couple simplifying radicals questions. I'm going to do this one, because that one has kind of everything together with it. Maybe we'll do one more as well. I'll do this one too. So when you simplify radicals, so first things first, you can only add or subtract things that have the same radical value. Same thing with variables. I can only add x and x. I can't add an x and a y. So in this case, I could actually add these two things together. I also have to make sure that all perfect squares inside what we call the radicand, the value underneath the radical, have been simplified. So inside of 18, what's the biggest perfect square that divides into 18? Chris? 9 and 2. Are there any perfect squares inside of 8? 4 and 2. And I'm actually going to add these together. So if I have 3 root 3 minus 7 root 3, it's the same thing as the expression 3x minus 7x. I'll get negative 4x. So similarly, we keep the radical value and we just subtract the numbers in front. So 3 minus 7 is negative 4, and I'll keep that root 3 on the end. I have 3 root 3's, I'm subtracting 7 root 3's, I now have negative 4 root 3's. We'll keep going here. I'm going to reduce the 9 to 3, and I will reduce this 4 by square rooting it to 2. This 2 remains inside the square root, and then I'm just going to multiply in front there. And I can actually simplify one step further here by adding 3 root 2 and 4 root 2. So if I have 3 root 2's and I add 4 more, I'm going to have 7 of them. So 7 root 2. Not allowed to add 7 root 2 and 4 root 3 or subtract them because they have different root values. Okay, we also did some foiling questions with these types of things as well. I'm going to let you guys review those on your own exam review package, and then you need to go through this process of simplifying any roots. But for the most part, like you would do a question like this by doing like firsts, outsides, insides, and then lasts, and then kind of expand from there. So when you multiply, so I'm just going to do the first piece with you here. When you multiply 2 roots together, you'll multiply the numbers in front, so 4 times 5, and then you'll multiply the numbers underneath the roots together and keep that underneath the root. So 2 times 5 will give you 20 root 10 for that first one. And then you can just continue multiplying and then simplify any roots just like we did above. Okay, so I'll let you guys work on some of those on your review package. Okay, exact roots using quadratic formula. This was one big one that we did, which was if you can't factor, then we try to use quadratic formula and we'll leave things in exact values. So A is 1, B is negative 2, and C is negative 2. I'm going to use the quadratic formula, which you will see is given to you on your package, or on your formula sheet in that little review topics package that I posted. So this is given. All you need to know is how to plug them in and simplify from there. And obviously you need to know how to use the you need to know to use the quadratic formula to find exact roots if you don't have the ability to factor. Okay, so just plugging these things in here. This was from grade 10 as well, and then we extended it to the grade 11 part by keeping it in exact form. So we'll get 4 plus 8, which will give us 12. Remember when you square something that you need to put brackets around it in your calculator, okay? Just be careful with that. And then from here we do the grade 11 part, which is we want to simplify the radical that's here. So I'm going to find the biggest perfect square inside of 12, which is 4. One of the things that you split this number into must be a perfect square. Perfect squares can be square rooted to get a whole number. So things that are perfect squares are 1, 4, 9, 16, 25, 36, and so on. Because every one of these I can square root and I'll get a whole number. So I'm looking to split this value up into something that falls within that list. If it doesn't, and you can't find any number that divides into your radicand, this number right here, then you leave it here and you just split into the positive option and the negative option. If you can go further, then you go further with it. So I'm going to square root the 4 into 2. And then from there, we will common factor the 2 out on top. So I'll be left with 1 and just a root 3 here. And then we look to see if we can simplify anything on the top that we common factored out with what's on the bottom, which in this case we can actually just cancel both of those 2's out. So we'll get a first x-intercept of 1 plus root 3 and a second x-intercept of 1 minus root 3. Okay, Last thing that we did in this unit, and I might also just take one extra minute at the end of this to review long factoring a hard trinomial, because that's important. Using the discriminant to predict intersection points and then actually finding those intersection points. There is a question on your exam that requires you to find intersection points, or on your exam review, sorry. Your exam review asks you find the exact value of the intersection points. You don't need to use exact values for intersection points. I'm going to let you guys use decimals for these. So don't worry about doing exact values in your exam review package for the intersection points question. So when I'm finding intersection points between a line and a quadratic, we have three options. We can have 2, 1, or 0 points of intersection. When I'm looking for the intersection points or looking to predict the intersection points, I always start by setting the line and quadratic equal to one another. The reason that I do this is because I want to find where they have an equal x and y coordinate, because that's where they cross, right? That's where they intersect. The x and y are the same for both functions. So I'm trying to find where those x's are equal. So that's why I'm setting the equations equal to one another. I'll move everything over to one side. So I'm going to move the 5x and the 11. And if I'm using the discriminant to predict, I will plug in a, b, c into the discriminant, b squared minus 4ac, at this point right here. So I'm going to plug in b squared minus 4ac. Which will give me 4 plus 60, which will give me 64. If this value is positive, this is telling you you have 2 points of intersection. If the value is equal to 0, you have 1 point of intersection. If that discriminant value is negative, you have 0 points of intersection. It's the same thing as predicting roots with a quadratic. From there, if I want to find the intersection points, I will continue from my equation here. So I'm going to continue off of this. Oh, this just stopped working. 1 second. Give me 2 seconds here. Okay, so we're going to continue with 0 equals x squared minus 2x minus 15. The options from here, after we've set both equations equal and we moved everything to one side, is I will factor, or I will use quadratic formula if I don't know, if I can't factor. So are there any two numbers that multiply to negative 15 and add to negative 2? Two numbers, they need to add to negative 2, multiply to negative 15. Negative 5 and 3. This is also easy factoring, so when x squared has a coefficient of 1, we can put these right into the bracket. So x minus 5, x plus 3. The x solutions are 5 and negative 3. We want to remember to switch the signs on those guys. We need the y coordinates of these x coordinates of the points of intersection. So I'm going to plug each of these back into either one of the original equations. It doesn't matter. If I found the correct x's, I should get the same y coordinate out of either of those two equations. So I usually plug it into the line. So I'm going to evaluate g at 5. But you can check in the other equation as well. That's a good check that you can do. So 25 plus 11 is 36. And then I'm going to evaluate g at negative 3 as well. So negative 15 plus 11 gives me negative 4. So the final points of intersection, 5, 36, and negative 3, negative 4. Again, if you wanted to do a check, I would check that 5 and negative 3, when you put them back in there, give you these same x and y coordinates. So they need to give you the same y's out when you plug them into the second equation as well. That will confirm that those points are on both equations. That's what we want, right? We want to know that they intersect at those points. So remember when I put them into the fraction or into the brackets, I'll put them in as like x minus 5, x plus 3. But when we take them out of the brackets, we switch the sign because we're looking for where, like the idea behind this is that if I have something times something equals 0, one of those two things or both of those two things could be 0 to make that statement true, right? So what makes x minus 5 equal to 0? Positive 5. And then x plus 3, negative 3 makes that 0. So we're solving for what's going to make that 0. Okay, the last thing that I want to go over, and I think everybody should take a look at this, even if you're not, if you're kind of doing your own thing and doing your own review, is factoring. And I'm talking about factoring a hard trinomial. So I'm going to give you an example here. Let me just make one up. Okay, and I want to factor, say y equals. How do I factor something like this? Josh?
Multiply A and C, and you get that, and then you figure out whatever, like, what times what equals negative 18, and then adds negative 7.
Okay, so in this case, this is long, hard trinomial factoring. You have to do a couple extra steps. What multiplies to A times C and adds to B? So what two things multiply to negative 18 and add to negative 7? Maya? Negative 9 and 2. This isn't as easy as just sticking these into the brackets like we did in the previous example. We must take the middle term and split it into these two terms. So we're going to split it into negative 9x and positive 2x. So I actually split negative 7x up into those two numbers that I found. And then we do factoring by grouping. I do this group and this group. We common factor from each. So I'm going to take out a 3x from the first group. I'll be left with x minus 3. And I'm going to take out a positive 2. Whenever I take out the number in the second set, I'll always take out the number with its sign. So positive 2, or if I'm taking out a negative, I'll take the negative out with it. I'll be left with x minus 3. I will know I'm on the right track if these brackets are the same. Then, out of this group and this group, I see that we have a common bracket. We're going to take that bracket out. And if I remove that from each term, I'm going to be left with 3x plus 2 in the second bracket. Okay? How do I check my factoring work? How can I check that this is correct? How would I check that that's equal to this? Jacob?
Can't you do FOIL?
Yeah. So you can FOIL this back out, and you should get this back if you've done it correctly. What's the x-intercepts here if this was equal to 0? What's the x-intercept for x minus 3? Abby? 3? How about for this one, 3x plus 2? Abby, you know it? Negative 2 over 3, correct. Quick way to do this, switch the sign and do this number over this number. If you're not entirely sure, you set it equal to 0, that expression in the bracket there, and just isolate for x. So then you'll divide out 3, and you'll get negative 2 over 3. And then you'll have your x-intercepts. Okay, I'll close it off there for Unit 1, and we'll continue with Unit 2 a little bit later in the class, okay?